the last one we talked about, and we will quickly run through it, is the sensor subsystem. And invariably what will happen is that you will have some conditioning or you have the, let us say this is the sensor module itself. The sensor module essentially takes energy of some form and converts it to electrical energy, so that then our electronic systems can work. So, that is the job that the sensor does. You will have a analog front end. The analog front end will include conditioning, will include amplification, etc., and this then goes to an ADC. This will go to the MCU. Sometimes this ADC can also reside in the MCU, right. So, this is a very simple look of the sensor subsystem. We are not going to spend much time on the or any time on the sensor subsystem, but this is just for completeness sake I showed it to you. So, very quickly what we did was worked our way through the different subsystems, and the reason we are doing this is for you to get a flavor of, okay, if I was an embedded system engineer, maybe these are the kind of decisions I will be called upon to make, right. So, some of it might look like, oh, we are jumping from connectivity to audio to charging, but that is also what a embedded systems engineer is expected to do when architecting a system like the one we are working on. So, we talked about the connectivity subsystem, the distinction between the analog and digital. Likewise with the audio subsystem, where again these are mixed signal subsystems, where we need to understand the distinction between the analog subsystem and the digital subsystem. And then we worked on 2-3 analog only or 100% analog subsystems. The first one was the charging subsystem. The second one was the power management subsystem. And in the context of the power management subsystem, we talked about both linear and switching regulators. The distinction, and again I keep repeating this point about trade off, right. You can say, oh, a switching regulator is better than a linear regulator. Yes, in terms of efficiency, but a switching regulator is more expensive than a linear regulator. So, should you go with a switching regulator or should you go with a linear regulator? That is a question for the system engineer to answer. Different applications might demand different answers, but once you have the underlying knowledge of, oh, what is the pro, what is the con, then you can weigh the trade off and say, for this application maybe this is the right use case. So, where you are driving an RF, you might say, actually RF I am particular about keeping that supply also clean, and anyway it needs a high supply, so efficiency is really not a problem, so I am going to drive it with an LDO. Whereas for the microprocessor, you might say that tends to take a lot of current and the voltage difference is so large that it is better to drive it with a switching regulator. So, these are choices that you will make as the system engineer. And then we talked about the LED subsystem. Again, these are all subsystems that offer the engineer problems or questions in terms of trade-offs between performance and price, between what you can perceive as user experience and price, right. All of us want the very best of everything for the user, but that also comes for a cost. So, and you can think of these as simple examples of illustrating that point. So, an LED intensity that does not change with battery voltage comes at a cost. Now, is it worth that cost? Again, a call for the embedded system engineer to make. And finally, we talked about the sensor subsystem, right. So, what we are going to sort of do next is maybe with this background, go back to our block diagram and think about now as an embedded system designer or embedded system engineer, what is my role, what am I expected to do, right. Let us try to wrap our heads around that based on all of the work we have done up to this point, right. We looked at the subsystems, and I think now it is again worth looking at how should the embedded system engineer view his or her role, what are the problems they are called upon to solve. So, when we started talking about this topic, we said one of the first things we want to nail is what are the problems that an embedded engineer or an embedded system designer is called upon to solve. So, let us go back to our block diagram, and in this block diagram, now you say, okay, I need a microcontroller, I need an audio subsystem, I need a connectivity subsystem, I need a power management subsystem, so on and so forth. There are so many different options in terms of where you can get these subsystems from, right. So, for example, a company like Qualcomm maybe offers these solutions. A company like Dialog Semi offers some of these solutions. A company like a Realtek or a company like a Broadcom, they all offer different portions of this solution. When it comes to charging and power management subsystems, you could get it from a Texas Instruments, you could get it from an Analog Devices, you could get it from a Realtek. There are maybe other companies that I am missing out, but it is possible now to say that okay, there are different people that offer solutions for each of these subsystems, and in some cases the combination of this subsystem, right. Now, the end user really does not care who is supplying what subsystem, that does not matter to the user. So, what matters to the user? So, let us try to sort of list the end user considerations. What all does the end user care about? You put yourself in the shoes of a customer and say, when I buy a product, what all do I care about? What I care about is performance. If the product says it will do something, it better do it. I care about how much I am paying for it. I care about the reliability of the product. I do not expect that I bought it today, it worked today, and tomorrow the following day it stopped working. That is not a great experience for me. I assume that it is an electronic product is going to last me a few years at the very minimum, right. These are the three things that a customer will care about. So, you can say that, okay, now as a embedded system designer, these are my primary considerations when it comes to selecting these chips. So, my job at some level, so now if I say for an embedded system engineer, say, my responsibility is to select the chip. My responsibility is also to integrate the hardware and firmware onto the product, which means I also have to figure out how to bring all of these chips together, both in the form of hardware and in the form of firmware / software, right. So, that is what I have to do, but while I do those, I have to keep all these considerations in mind. So, I have to keep thinking about, for this performance, for these algorithms that I want to build, is this the most optimum solution from a price and reliability point, right. So, there are some performance aspects that I cannot give up, maybe some I can afford to give up. Now, it is a question of saying, okay, let me open up each of these data sheets, let me try to put together a table comparing the different parameters of interest to me and see which ones make the cut, and once they make the cut, which is the one that offers me the best price advantage, right. So, that is one way that an embedded system engineer can think about the problem in front of them, right. So, the other aspects that you would consider in addition to performance, price and reliability is, you would also say, okay, what sort of package does it come in, because, so now this the end user does not care about. Let me clean this up a little bit here. So, these are the end user considerations. Now, for the and on this side let me list down the considerations for the embedded system engineer. So, there is obviously price, performance, reliability, right. There is also, in terms of, we talked about battery life, right. Now, not battery life, we talked about the fact that these are portable devices. Portable devices means, again, you have to keep recharging the battery, and in some cases now you look at a Bluetooth headset, you want to say, if every day if I have to come back and charge it, that's not an experience that I really like, right. So, how often I have to charge the battery, in my mind is something I associate a certain value with, because I say, no, my life I don't need to really change something, I just take this, put it on, it works, and rarely I have to charge. Versus every day I have to go charge, I will say, okay, oh, yesterday I forgot to charge, today I can't use that product. Over time the habit of using that product goes away, right. So, there is, in addition to price, performance, reliability, so what the user will also care about is battery life, which means that what the embedded system engineer needs to care about is power consumption, because power consumption correlates directly with battery life. The end user might not care about the packages of the chips, but the embedded system engineer will care about it, because part of the embedded engineer's responsibility is to say, no, I have to integrate the hardware onto the product. Now, if I have this product is interesting, but it comes in a very complex BGA package, then now I have to worry about what is the reliability of the assembly, or what is the reliability of the process by which I make the product. So, that also becomes a part of the embedded engineer's trade-offs. So, the type of package or packaging considerations, and also the form factor. Now, for example, you can say that, I am building again Bluetooth headset, let us say in the form of an earbud. I have only so much space, and in that space I have to put a battery, I have to put this PCB, I have to maybe put some other components as well, which means that the amount of real estate available for me is extremely small. Now, if that is all is the real estate available, if my MCU is a TQFP package or some package which translates to a very large size, and it ends up blowing up my PCB A size, that is not acceptable to me, because it is important for me to meet the form factor that my end user expects. So, somewhere there is a form factor consideration for the individual chips and hence for the PCBA itself. So, now what an embedded system engineer does is, the embedded system engineer does chip selection, and then he or she integrates hardware or firmware onto the product, and while they do this keeping in mind that there are these 6 parameters that are important, namely price, performance, reliability, power consumption, packaging considerations, and form factor. So, and engineering is the elements of engineering which are exact, but decision making in engineering is almost always a trade-off, where you say, okay, I have different parameters, I have to weigh them and see which is going to give me the best bang for the buck, right. That is a continuous state, a near permanent state if you are doing any architecture development. So, again, the decisions to be made are with respect to, should I use a TI chip, should I use an ADI chip, should I use a chip from somebody else, and that decision is made keeping in mind, okay, what is the price, what is the performance, what is the reliability, will the user suddenly see some problem that I get a field written because I chose this chip instead of that chip, what is the power consumption, what is the form factor, what is the packaging consideration, so on and so forth, right. So, the again, for the system engineer, it is that realm of operation where you say, okay, Now I have 6 different considerations that I have to keep in mind. With these 6 different considerations, I am going to go about the process of chip selection and chip and firmware integration, right. What we will try and do is say, okay, if this is the path we want to take, maybe we will take something like a battery charger as an example and say, okay, I want to design a charging subsystem, right. Now, I have these 6 parameters. In the specific context of a battery charger, what does reliability mean? What does performance mean? Right? And now, okay, if I understand what those two mean, now what document gives me information on the other things, and how do I parse such a document? How do I read it? How do I understand it? Right? And okay, I also don't just want to be, for me to be an efficient chip selector, I have to understand how that subsystem works so that I am able to evaluate different chips properly. So I need an understanding of that subsystem operation. Then I need to understand what specific figures of merit or parameters I should monitor in the context of these points of interest, in the context of performance, in the context of reliability. What are the equivalent figures of merit or parameters of interest for the battery charger, and how do I look at the data sheet, understand it, to be able to get answers to all of these questions, right. So maybe that is what we will try to do next, and hopefully that gives you a flavor for how you might, somebody who architects embedded systems approaches the problems.